Hi everybody. First, I want to pick up where we left off last time, because I felt like I rushed it a bit. So remember, we were talking about this idea of a density of states, and what we're going to do is we're going to try and count up. We want to find big omega, and we're going to try and count up all the available states that exist for some gas of n particles, non-interacting n particles that have a total energy between E and E plus dE. And we've written that down here as a big honkin' integral. And so we're going to integrate over the spatial coordinates of all the n particles, and we're going to integrate over the momentum of all the n possible particles. And the constraint, which I probably should really write as a delta function, but I've written it out front here, is this idea that the energy has to be between E and E plus dE. So if we do the spatial integrals first, since these are non-interacting particles, we can just do that. Each one of the spatial sets of variables for a particle gives us a factor of the volume, so we end up with v to the n out front. And then we are left with this idea that we're going to somehow integrate over momentum space with the constraint that the total energy is going to be between E and E plus dE. All right. Now, remember, this is the part I rushed through a bit last time. Remember that we can think about the momentum of each particle as being the sum of the square of the momentum of each particle is the sum of the squares of the components of the momentum. Really, the total momentum of everything, the total p squared, right, of everything is going to basically be the sum of all the px squareds, the py squareds, and the pz squares of all the particles. And if we say the particles have mass m, we can say that 2me, the total energy, right? We're going to add up the kinetic energy of all the particles. That has to be equal to the sum of all the p squareds over each particle, right? We're going to add up all the particles, the p squared of each particle. That's going to give us twice the mass of each particle times the total energy. Now, this is an interesting thing to think about. What it tells you is that you could have a situation, for example, where all of your energy E is crammed into one of the particles and the others have almost no momentum. Or you could have a situation where this total energy E is spread out among all the particles, right? But we're summing up to n. We're going to sum over all these particles. Now, the total dimensionality of this space here, we've got a 3n dimensional momentum space. And that means that really there's going to be, because there's an x and a y and a z for each of the particles, that means there's going to be 3n terms in this sum, right? So if we're constraining ourselves to have some energy between E and E plus dE, we're really thinking about the surface in that 3n dimensional space that is basically a sphere in 3n dimensional momentum space, right, where the radius of that sphere is given by, basically the magnitude of the total p, right, is going to basically be the square root of 2me. Now, just from, if we're willing to throw away, because we've got a proportionality sign here, if we're willing to throw away that prefactor, we can just pretty quickly say, all right, if I've got a sphere of radius this, and there's 3n dimensions, then the area of that sphere is going to be 3n dimensions over 2 minus 1, because the volume of the sphere is going to be 3n dimensions over 2, right? So what we find here is that omega of E dE has to be proportional in some way to volume to the n, energy to the 3n over 2 minus 1, right? And then we've got the dE, which means that big omega is going to basically be the integral of little omega, the density of states, dE. And if we can integrate this whole thing with respect to E, and it's very simple, we're going to have, it's going to be some constant, some normalization constant that I call B, times V to the capital N times energy to the 3N over 2. All right? And that is going to be big omega of E. Now, rewriting that for a second here. All right, so I've rewritten that, and my dog has stopped making sounds. So that's omega, and remember, S is K Boltzmann log of omega, right? So in principle, we can find the entropy. The entropy is just this thing. Now, one thing I could do is I could write this out term by term, and I could say it's K Boltzmann natural log of B plus N natural log of V plus 3N over 2 natural log of E. I could do that. That's actually pretty bad practice. Now, you probably already know why that's bad practice, because what I'm doing here when I write it this way is I'm actually taking the natural log of things that have units. And you really should never do that, right? I really ought to combine all of these things in such a way involving B here so that the argument of my natural logs is dimensionless. And we will do that. But I did want to point out a couple of things. It's worthwhile looking to see how the entropy actually scales with particle number and with volume and with energy in a system like this. Okay? Now, let's stop there for a second. We'll go on to a new slide. The important thing here that I should have highlighted from before is that the entropy, right, I mentioned this before, is a function of the energy, the volume, and the particle number. Those are the so-called natural variables for the energy, right? So now we're going to consider two systems. We are going to have a system that is like this, and we're going to have some kind of a partition between them, right? And on this side, we're going to have energy E1, volume V1, and particle number N1. And on this side, we're going to have energy E2, volume V2, particle number N2. And we are going to keep this partition in place, but we are going to allow energy to exchange. All right, so I'll stop being cute. Allow energy exchange there. So what's going to happen? Well, you kind of have, so what I'm saying here is I'm going to allow heat to go back and forth between these things. Now, we have not rigorously defined temperature. In fact, we're about to do that. But you sort of know intuitively what should happen. One of these sides is going to be hotter than the other, and you expect energy to flow in some way from the hot side to the cold side until eventually these things reach some intermediate temperature, right? Now, if we want to think about this from the entropy perspective, what we want to do is want to say in equilibrium, if these two sides are in equilibrium with each other, S equals, the total S is maximized, right? So that means that any little change in S should be 0 if I allow there to be some little tiny deviation from equilibrium, okay? So what does that mean? Well, I can write this down. I can say any change in entropy here from the energy exchange process, right? That's going to look like partial S of system 1, partial energy of system 1, dE1. So this is the energy change in system 1 due to the transfer of energy into system 1, right? And the total entropy change is going to have the contribution from system 2 also. So we're going to have partial S2, partial E2, dE2. Now, I'm going to write a couple of other things on here. These partial derivatives, this is a standard notation thing in thermodynamics. Because there are so many variables and you're dealing with multiple variables, it's convention to write down which things are being held constant when you're taking partial derivatives. In this case, you're just reminding yourself that the other variables in the problem are volume and particle numbers. So we're going to write down partial S1, partial E1 at constant V1 and N1. and we've got partial S2, partial E2 at constant V2 and N2. All right? And I just told you, if we're really in equilibrium, this little tiny variation in S has to be 0. Now, we can do better than that. We know that if this whole rest of this thing is isolated energetically, there's nothing else going on, the only thing that can happen is these two systems trade energy with each other. That means that dE1 plus dE2 is 0, right? Any energy gained by system 1 has to come from system 2 and vice versa. So if we substitute that in, I can rewrite this and I can say delta S is actually going to be, let me see here, partial S1, partial E1, dE1, right, minus partial S2, partial E2, dE1, right? Because I'm saying dE2 is minus dE2 here is minus dE1. So if that's true, and this whole thing has to equal 0, and dE1 is arbitrary, then that implies, as we go on to the next slide, we have to have in equilibrium therefore partial S1, partial E1 at constant volume 1 and particle number 1, has to equal partial S2, partial E2 at constant V2 and N2. All right. And of course, you could generalize this to a third system, and you would find that if all of these things are in equilibrium, all of their partials of S with respect to E should be equal to each other. Boy, that sounds a lot like temperature, but it's not exactly temperature. In order to make sure that things actually flow in the right direction, it turns out that we define the thermodynamic definition of temperature is actually given by 1 over the temperature is defined as partial S, partial energy at constant volume and particle number. All right. Why 1 over T? Well, it's worth thinking about. Imagine that you want to make sure that basically that heat actually flows from hot things to cold things, right? So imagine that you have two systems that are at slightly different temperatures that are brought into contact, right? And that energy is going to flow into system 1. So suppose dE1 is going to be greater than 0, right? The energy is going to flows from 2 into 1, right? And we're going to say that that happens spontaneously, so that's going to imply that ds has to be greater than 0 for this to happen freely. All right. So what does ds look like? Well, ds is going to be from our definitions that we just had. It's going to be 1 over T1 dE1 plus 1 over T2 dE2. But remember, dE1 and dE2 are the same in magnitude and the opposite in sign. So I could just as well write that this is going to equal 1 over T1 minus 1 over T2 dE1, right? And so I said ds is positive, dE1 is positive, so this is only going to happen, energy can only flow like this if 1 over T1 minus 1 over T2 is greater than 0, or T2 is greater than T1, right? So this works out. This definition does in fact imply that energy flows from things at high temperature to things at low temperature. So moving on for 1 second here, we can also see that for each individual system, we actually do have that dE is T ds. All right? And so this agrees with our ideas about heat transfer. Right? From our first law, we basically said that you can have the energy coming from the heat or from the work, right? And this says that this is what the heat transfer part looks like. Okay? Now, let's move on. Let me pause for 1 second, and then we'll move on here. Okay. So we are going to consider now, we just did the system where the situation where two systems are allowed to exchange energy. Let's do a more complicated version of this where we're going to allow our little partition to actually move. Those are supposed to be rollers. So again, we're going to have energy 1, volume 1, particle number 1, energy 2, volume 2, particle number 2, but we're going to let the partition move. So can exchange energy and volume. That's kind of funky, but you can imagine it happening. You can certainly have a thermally conductive partition that's able to slide back and forth here, right? So what happens in that case? Well, the argument is very similar to what we just did. We again say that the change in entropy, if we're in equilibrium, right? So sorry, I'm having issues with my app here. So in equilibrium, delta S has to be 0. But what is delta S? Well, it's going to be partial S1, partial E1 at constant V1 and N1, like before. dE1, that's the heat transfer part for system 1. And then, of course, we're going to have what we already had, partial S2, partial E2, dE2, right? But now we're also going to have plus, because the other way the entropy can change now, if we can exchange volume, is we're going to have partial S1, partial volume 1 at constant E1 and N1, that's new, dV1, plus partial S2, partial volume 2 at constant E2 and N2, dV2. So we already had these two terms, and now we've added these two terms. Again, we have that the total energy is conserved, right? Which means that dE1 has to equal minus dE2. And similarly, when we move the partition back and forth, d volume 1 has to equal minus d volume 2. Any volume gained by system 1 has to be lost by system 2. So if we regroup everything, we have delta S equals partial S1, partial E1, V1, N1, minus partial S2, partial E2, constant V2 and N2, all of that times dE1, right, plus partial S1, partial V1, constant E1 and N1, minus partial S2, partial V2, constant E2 and N2, and all of that times dV1. And remember, dE1 and dV1 are totally arbitrary little variations, and they're completely independent of each other. They could be anything, right? And we're saying that this whole thing has to equal 0 if we're in equilibrium. So what does that imply? That implies, just like before, therefore, partial S1, partial E1 at constant V1 and N1 must equal partial S2 partial E2 at constant V2 and N2, which is another way of saying that 1 over T1 has to equal 1 over T2, right? We already knew that. These two things, if they're in equilibrium, have to be at the same temperature. But now we also need partial S1 partial V1 at constant E1 and N1 has to equal partial S2 partial V2 at constant E2 and N2. All right, so this is this new thing we have. Now, what does it mean? This has something to do, this equation here has something to do, these partial derivatives have something to do with how the entropy changes with volume, right? So you have every reason to think, at least for a gas, that if the volume goes up, generically speaking, the entropy should go up, because the entropy has to do with the number of available microstates. And if you make the system larger, there really ought to generically be more microstates available. Certainly for a gas, that's kind of obvious, right? So it turns out that we are going to define pressure involving these terms, right? So it turns out that the thermodynamic definition of pressure, note that this is not, I already told you earlier that pressure really, we know microscopically from the statistical mechanics point of view, pressure results from a zillion microscopic collisions of little gas molecules off of the walls of a container. But the thermodynamic definition of pressure, which you can derive independent of any of those microscopic details, is given by the pressure is defined as temperature times partial S partial V at constant E and N, right? Now, I'm telling you that that's the definition of pressure, but does that agree with our reasoning? Well, now, again, if we consider an entropy change from bringing two systems together, right? My handwriting's getting really bad. I apologize. So if we consider the entropy change from bringing two systems together, just like we did before, where we figured out that the temperatures had to be like this in terms of the definitions, you can do the same thing, and we can basically follow that same reasoning. And what we're going to find is that the entropy change, say, for system 1, when we bring these two systems together, it's going to have two pieces. It's going to have a 1 over T1 dE1 piece, which is basically the piece we had from before. That's the heat transfer piece if we allow these two systems to talk to each other. And then it's going to have another piece, and that other piece is going to be, from this definition, it's going to end up being P1 over T1 dV1. Okay, if we just plug in. And that's kind of interesting. If we rearrange this, right, and we drop the one subscript because we're just talking about one of the two systems now, what you're going to find if we just play games is we're going to find that dE is going to end up equaling TdS minus PdV. And remember, this looks an awful lot like dE equals d bar Q plus d bar W, where I said before, one way you can have a work here is you can have that be minus PdV, right? So it's very, very tempting to basically, it's not just tempting, this is how we do it. This is how we define the pressure, and we can actually look, and then we can basically say that this is this first term here, the TdS, is the heat transfer piece. All right, so this is the first law, falls out of this with our definitions. So that all makes nice sense. And again, the idea here is that we're assuming that the entropy is at a maximum, and we're worrying about changing the system in some way. Changes to the system, small changes to the system in terms of its natural variables should not really change the entropy anymore. And if the ds has to be 0, and that's how we derive these things. Now we can do this one more time, right? Now, let's do the ultimate version of this, at least as far as a gas is concerned. Now we're going to have like a porous membrane, which, by the way, can move. Okay, so it's like diffusively porous. It doesn't have like giant gaping holes in it, but somehow particles can go back and forth. And so again, we got system 1 and system 2, and they can exchange energy, volume, and particle number. Now we can do everything, right? So if you do that, you can do the same derivation yet again. And for equilibrium, you're going to find, here, surprise, surprise, partial S1, partial E1, constant volume and particle number is going to equal partial S2, partial E2 at constant volume and particle number. So that's just, again, 1 over T1 has to equal 1 over T2. This is all derived, again, assuming delta S equals 0, right? But now we're going to not just worry about energy, and we can do the same thing with volume, and we're going to find basically that P1 has to equal P2. That's not a big surprise. The new one we're going to find, actually, though, is partial S1, partial N1. Right, now we're going to let particle number change at constant E1 and V1. Has to equal partial S2, partial N2 at constant E2 and V2. Right. What on earth is this quantity, this partial S with respect to N? And again, you can kind of get this idea that well, it's hard to have a lot of intuition for this. It turns out we're going to define the thermodynamic definition, the chemical potential. This is a somewhat mysterious, at least for many people, quantity, because you're very familiar with temperature and you're very familiar with pressure. I'm going to try and convince you you're actually rather familiar with chemical potential. You just never think about it that way. But we're going to define the chemical potential, mu. Don't know why it's abbreviated mu, no idea. Is defined as minus T partial S partial N at constant E and V, right? That is the definition of the chemical potential. Now, you can, so the whole point is that if two systems can exchange particles and they're in equilibrium, then mu1 has to equal mu2, right? Their chemical potentials have to be equal. So you can do the same kind of reasoning we did before and ask if ds total must be greater than 0, and we allow particle, like we're going to consider two things with tiny differences in chemical potential, right? We're going to allow particle exchange, and we're going to have to, the only stuff that's going to spontaneously happen is the stuff where ds total is greater than 0. That's going to, if we play with that, we're going to find that ds total, if we actually go through the same sort of argument, it's going to end up equaling mu2 minus mu1 all over T, because if we're in equilibrium, the temperatures are the same, right? So T1 and T2 should be the same. dN1 there. So what does this mean? If dN1 is greater than 0, then mu2 must be greater than mu1. Or in other words, particles diffuse from high mu to low mu spontaneously. That's the thing that happens when you have a difference in chemical potential. So if you have a difference in pressures, volume actually flows from the system. The system that has high pressure gains volume, right? If they're allowed to exchange volume. If you have a temperature difference, the system that has high temperature loses energy. The system with low temperature gains energy. And similarly, if you have two systems with different chemical potentials, the system at lower chemical potential will gain particles. The system with higher chemical potential will lose particles. So it's challenging to get a lot of physical intuition about the chemical potential. One example of something where you do have some experience, I guarantee it, at some time in your life, right? Imagine a bottle of perfume, right? Or something, maybe less smelling and less pleasantly smelling. I don't know. So here's a little tiny bottle with a little stopper in it of perfume, right? And it's full of perfume molecules, very dense. And I'm trying to color it in, and my stylus is not letting me do that. There's a whole ton of perfume molecules. Now I'm going to take the stopper out, right? And those perfume molecules will start spreading out into the room, okay? And one way to think about that is that if we talk just purely in terms of entropy, before with the stopper in, there were, the number of microstates available to these molecules was restricted to the ones that live inside the bottle. As soon as I pull the stopper out, now these molecules are going to try and explore all available microstates, and they're going to move out of the bottle and go all over the place, right? And that now that they have more, more space equals greater omega equals greater S, and so that's just gonna happen spontaneously. Another way to think about this is to say, in the bottle we have high chemical potential for the molecules, and outside the bottle we have very low mu for the molecules. And so as soon as I remove the stopper, the molecules are going to diffuse from the region of high mu to the region of low mu. And if I wait a long time, I will eventually have a uniform density of molecules out here and in the bottle. And molecules, there will no longer be a net diffusion of particles. Molecules will leave and they'll enter, but the average number of molecules per volume will just sit here, right? Assuming the whole thing's at uniform temperature and pressure. So one way of thinking about the chemical potential is you could think about it as chemical potential as a driving, I hate to use the word force because that's not really an F equals ma kind of force, but it's the driving force for diffusion, right? That's one interpretation of chemical potential that people tend to understand. Now, there's another way of thinking about chemical potential. Another way of thinking about the chemical potential is to actually rewrite our entropy change again with n this time, right? So if you do that, what you find is that what was the entropy change of some system, I'll drop the subscript just for clarity, we can say ds if we let the system actually exchange energy and volume and particles, right? We're going to end up with something that looks like 1 over T dE, right? That's the change in entropy due to changes in energy. P over T d volume, right? That's again from our definition of pressure. And now we've got one more term, and it's going to look like minus mu over T dN, just from what we wrote down before on the previous slide. So if we put all that together, basically we're going to multiply through by a t and rearrange things. We now have dE, hey, this is going to look like the first law, and it is in fact a generalization of the first law where now we're going to let particles move around too. So we can change the internal energy of a system in a few different ways. We have TdS, which is of course heat transfer still. Minus PdV, so that's going to be the work, right? That's the work done on the system is minus PdV. And then we're going to have one more way to change the energy of the system, plus mu dN. Interesting. So we can change the internal energy of the system by transferring heat, by changing its volume and doing work on the system, or by changing the number of particles in the system. So this is another interpretation of the chemical potential. Another interpretation of mu. It's basically the change in internal energy of a system when one particle is added at constant S and V. That's a little bit harder to think about. I mean, you can. I will tell you later in the course, we're going to learn when we talk about fermions, we talk about Fermi-Dirac statistics, then it will actually look very, very clear why that's a useful way to think about the chemical potential. But I just want to point out this is, a second interpretation of chemical potential. If you really want to learn more about this, we'll talk about it more later in the class. But I have an article on Canvas called "The Elusive Chemical Potential" by a fellow named Bayerlein, who has also written a statistical mechanics and thermodynamics textbook. But this article is from American Journal of Physics, and it basically rattles off several different ways of thinking about the chemical potential that are maybe useful to students, right? Sometimes it's very good just to hear the same thing said in different ways, and it's good to see that you can think about the chemical potential, which is much less intuitive in many ways than the temperature and the pressure. It tries to give you several different ways to think about it. One last anecdote before we move on about the chemical potential. When I was a grad student at Stanford, Bob Laughlin, who has now gone off to win the Nobel Prize for the fractional quantum Hall effect, Bob Laughlin was teaching a class that I was taking, and he made the statement once regarding Rife and the chemical potential, that Rife did not understand the chemical potential when he wrote the book, and he doesn't understand it now. Pretty harsh statement. What it really meant is that Bob Laughlin did not like the way Rife explained chemical potential in his textbook. So if you find Rife's description of chemical potential to be not so great and not very clear, you're not alone. Very famous people have also not really liked the way Rife talks about chemical potential. All right, let me stop there, and we'll pick up with a clean slate in a minute. Continuing, I want to say a few words about reversibility. So clearly a truly reversible process is one where the entropy change of the universe is zero, right? That's one where you can completely run something forward and backward, and there's no entropy change whatsoever. And that's one definition of reversibility. Now, an irreversible process and by definition, there's some delta S of the universe that is greater than zero. And let me give you an example. So if you talk about having a piston and you want to compress the gas inside a cylinder, you can do this in a reversible way. You can push the piston in very gently and very slowly, and you can compress the gas. And if the piston is frictionless and you do this very nice and slowly, then the system is always in some sort of local instantaneous equilibrium. Even actually if you allow some heat transfer between the gas inside the piston and the outside world, this is not necessarily an irreversible process for the universe as a whole, right? You can run it backwards. You could imagine if you compress the piston and you allow energy to leave the gas in the form of heat transfer to the outside world, that can be okay. In say an isothermal process like we discussed. And if I imagine gently pulling the piston back the other way and letting heat transfer from the outside world into the cylinder, I am basically undoing what I did before, and the total entropy of the universe ends up being unchanged. What's an example of an irreversible process? Well, that's if you imagine having, say, friction in the piston cylinder walls, right? That's one example where you are attempting to do work, you're generating heat, not from heat transfer, but you're generating heat by somehow irreversibly transferring energy from your effort into the disorganized internal energy of the walls of the system and of the gas, right? Or if you did something like a shock wave in the gas, that would be something that would be irreversible. Or even if you did something like vent gas into an empty room, right? The actual, if I just open a valve on a gas tank into an empty room and the gas pours out of the gas tank and fills up the room, the actual entropy change of the universe is greater than zero. And so that's an irreversible process. That there's no nice way to undo that. All right. Now, one of the big questions is sort of a philosophical question, is that the microscopic rules, microscopic physical laws, seem to be time reversible for the most part, with a couple of little tiny exceptions in high energy physics. It seems like I can run Newton's laws backwards and there's no problem. Or in fact, even in quantum mechanics, let's ignore conceptual issues about wave function collapse for a second. The idea here is that if I really knew the microscopic initial conditions of everything, I can run either Newton's laws or the Schrodinger equation forward in time or backward in time, and everything evolves just fine and nice and smoothly. So the big question is, how do you get irreversibility from time reversible physical laws? Now, Boltzmann, this is something Boltzmann struggled with literally the entire second portion of his career. He talked about something called the H theorem, which was basically a fudge about trying to somehow end up with irreversible macroscopic dynamics, even though the microscopic stuff is reversible. I can tell you how this actually ends up working on a practical level, right? The trick is essentially sensitivity to initial conditions. So in our favorite now overused example about if I vent a gas, here's my gas cylinder, and I'm going to vent that into the room, right? There's nothing wrong physically with arguing that you could have the gas molecules later obey the time-reversed version of those trajectories and have all the gas in the room eventually end up back in the bottle. Microscopically, that's allowed. Why do we never see that? We never see that because it would be incredibly unlikely. It would require some weird, crazy conspiracy where everything ends up with exactly the right initial conditions for the gas molecules to go backward into the bottle. And that, in some sense, the likelihood of that happening is infinitesimal because the sensitivity to initial conditions of the chaos involved in the motion of all the molecules is such that it's practically impossible to have that happen. Another analogy would be if I throw, here's a pond, and I can throw a rock into the pond, right, and I send out ripples. There's nothing in the laws of physics that says it's forbidden to have a bunch of ripples start out at the edge of the pond, converge on the middle of the pond, and spit the rock back out. That would all be allowed from the conservation laws and from the microscopic equations of motion, but you all know that that sounds completely absurd, right? You'd have to have some crazy conspiracy of initial conditions at the edge of the pond in order to set up that circumstance. So the macroscopic irreversibility comes because you'd have to have, it comes because we're able to pick special initial conditions, right? So the real philosophical question, in some sense, is how come S of the universe is so low, right? If the initial entropy of the universe wasn't crazy low, then we would never be able to pick special initial conditions, and we would never be able to see this issue of macroscopic irreversibility. That's a big philosophical question, and we'll return to it at some point later in the course, but I just wanted to give you some idea about where this comes from. Now that we've talked a little bit about entropy and the conditions for equilibrium, and we've really done the first law in a serious way, I also want to return to the third law of thermodynamics, just to remind you what this is. Basically, remember, S is K Boltzmann log, number of microstates, number of ways to do some macroscopic thing. So the third law, as originally conceived, it was that by basically Nernst in 1906, it's that S has to approach 0 as T approaches 0. It's been more recently amended, actually, that really S has to approach some small value as T approaches 0. So where does this come from? Well, the whole point is that if there is a real ground state for your system, I mean, we now understand this from the quantum mechanics side, right, or from the statistical mechanics side. If there is a ground state, then at T equals 0, you get there, right? You end up in, there's no energy available for excitations at T equals 0. You end up at omega equals some single unique ground state. And so clearly, therefore, S approaches 0 because log of 1 is 0. Now, the one caveat here actually is you can have, in real life, you can have a situation where the ground state is degenerate. That's pretty rare, but it happens actually in systems like ice. You can have a case with the degeneracy could be like little g, in which case then S as T goes to 0 would approach K Boltzmann log G. All right. We've talked a lot about entropy now, and something I didn't mention before, but it's probably occurred to you, how do you ever measure the entropy of something, right? It's a little bit like the internal energy. How do you measure the internal energy? There's no internal energy meter you can buy at Lowe's or Home Depot. There's no entropy meter you can buy at Lowe's or Home Depot. How do you infer? I've been telling you that these things are physically meaningful concepts, and yet you can't measure them directly. Well, it turns out you actually can experimentally determine the entropy. There's a way to do it, and that way involves the heat capacity or the specific heat. So that's what we're going to talk about next. Heat capacity. This is a term that, of course, like others, comes from back in the day when people thought heat was some kind of a fluid and you had to hold on to it. All right, you had to, every material object acted as a container for this fluid called heat. So how should we think about this? We're going to have some system, and we're going to have it be thermally isolated from the rest of the world. So I don't know how to draw that, but here's the system. It's thermally isolated from the rest of the world. And it starts out at temperature T. Now, I just said it was thermally isolated, but it has a temperature. What does that mean? Well, you can think of it a couple of ways. You can imagine, gee, maybe in the past I actually brought it into contact with some big reservoir that was at temperature T and let it come to equilibrium. Or you can imagine that, I thought about fictitiously in an ansatz kind of way, dividing the system into into two systems, and I let them come to equilibrium with each other, right? But the point is, this thing starts out at some temperature T, and then I consider add an amount of heat and add an amount of energy via heat transfer. That's the more precise way to say it, right? So I dump in some little bit of energy, which is actually going to go in the form of TdS, right? That's my heat transfer piece. I'm going to dump in a little bit of energy. System re-equilibrates if I wait a long time. Remember, thermodynamics doesn't really tell you how this happens. It just says it deals with equilibrium states. So we're not going to talk about the non-equilibrium processes right now. We're just going to say we're going to wait a long time, and this system will eventually return to some kind of thermal equilibrium. That is the irreversible, well, not the irreversible, the macroscopic irreversibility of what goes on there, right? Somehow the thing actually redistributes energy among its microscopic degrees of freedom and eventually comes to some new effective temperature. And so what we're going to do is we're going to basically say that, you know, T new, if we added energy, right, T new is going to be greater than T old. And so how should we think about this? Well, it turns out that delta T, right, the change in temperature, is going to be basically the heat transferred divided by some quantity that we will call big C, and this is the heat capacity. So if something's got a huge heat capacity, then I can dump in a certain amount of energy and its temperature won't go up by very much. If something has a tiny heat capacity, then it doesn't take very much energy transfer in order to boost its temperature a lot. All right, writing this more formally, we're going to do this at, under some conditions, right? We're going to do this at constant little y. I'm not telling you what that is. It could be constant volume, you know, could be pressure, could be, you know, other, you know, constant magnetization. There's different ways you can think about this for different systems, but we're going to have hold some parameters y constant, right? And so what we would say is that rearranging things a little bit here, right, we would say the heat capacity at constant y, which can depend on the temperature and obviously has to depend on whatever I'm holding constant. That is given by T partial S partial T at constant y. Okay, that's just sort of the differential form of this expression up here. Now, what should I say about that? Let me rewrite that. Hang on one second. Okay, so my capital C here, this is clearly the heat, this is the heat capacity and it's extensive. There's two ways you can tell it's extensive. One is that T is an intensive parameter, S is an extensive parameter, and so clearly the heat capacity as defined here is proportional to some extensive thing, so it has to be extensive. The other way to realize it is, imagine I take a certain amount of heat and I add it to, say, 1 gram of water. And now imagine I take that same amount of energy and I transfer it to a kilogram of water. Clearly, in the 1 gram of water case, the temperature of the water is going to go up a lot more, right? So you can tell that by having more material, that the heat capacity has gone up. So the heat capacity is an extensive thing. Now, very often, we will define something like, you know, it's a lowercase c, right? And that's going to be something like 1 over the number of moles, say, of stuff. This is basically 1 over capital N times T times partial S partial T at constant Y. This would be the molar specific heat. So if that's the difference, you know, sometimes I'll try to avoid being sloppy, but the heat capacity is the extensive property. The specific heat is where you basically, the specific heat is some flavor of, you know, C divided by the number of particles, right? Whether that's in the form of the number of moles of particles, whether it's in the form of the mass of the stuff, right? That's the specific heat.
And this is an intensive quantity now. The specific heat is the intensive version of the heat capacity because we've normalized it by how much stuff you have. All right? Now, I want to point out two subtle things here. One is the value of the heat capacity really does depend on what we're keeping constant. So, let's consider the case of a gas, right? And we can talk about a constant volume. So we're going to basically have the gas in a box, and we're going to dump heat into it. We're going to transfer energy via heat into it. At constant volume, we'd have some kind of heat capacity at constant volume. We can have the case where so here's just a box, right? Then we can have the piston case where the piston is free to move, and this would be the case where we have constant pressure instead of constant volume, right? We're going to add heat, we're going to add energy to the system and keep the pressure constant and ask how much does the temperature rise, right? And this is the heat capacity at constant pressure. So it's worth thinking about what's going on here, right? So in the constant volume case, all the energy that you add, all the delta energy goes into E, right? All of the energy you're dumping in goes directly into the internal energy somehow. But in this case, some of the energy goes into moving the piston. So it doesn't all end up in E. So the amount that ends up in E is less, meaning the temperature rise should be less, right? Because the energy is ending up in other places than inside the gas itself. And that implies that Cp should somehow be greater than Cv, because the temperature rise is actually going to be smaller. And if you recall from our previous slide, that when the temperature rise is smaller, that means the heat capacity is bigger. So somehow Cp, the heat capacity at constant pressure, has to be greater than the heat capacity at constant volume. So that's interesting, and we're actually going to derive what the difference is right now for a simple case involving the ideal gas. We can, and later, like in a couple of days, we're going to derive what happens in the completely general situation, right? Where we want the apparatus of thermodynamics is going to let us actually figure out in complete generality what the relationship is between Cp and Cv for all materials. It's pretty remarkable, actually, that we can do that independent of kind of the details of what things are made of. Now, the other subtlety that I want to get to here. Remember I said that Cv, for example, was T partial S partial T at constant V, right? Remember I told you that the original natural variables for S were E, V, and N. So this kind of partial derivative with respect to T is a bit tricky. Right, this is going to be the prelude to we're going to learn how to deal with these. Essentially, it's a problem of multivariable calculus, and we're going to learn how to deal with it very, very shortly. But it's actually an interesting point that it's not a trivial thing that we're taking a derivative with respect to a variable here, but it's not one of these so-called natural variables of S. All right. Now we happen to know for the constant volume case, we're in good shape. We know that the amount of heat we're adding in, the amount of energy we're transferring via heat, because we're constant volume, there's no work term here. So then we know that just has to equal dE. I just said that. And from the first law, we know that this is basically just TdS. So I can think about, in some sense, just considering my changes all happening with respect to temperature at some constant volume, and then I can write partial E partial temperature at constant volume is going to equal T partial S partial T at constant volume, pardon me, which means this is Cv, right? Okay, so the other point I wanted to make about this is if we actually know the heat capacity, this is how we're going to experimentally determine the entropy. All right, so you can imagine performing, so if you actually want to find S, right, of a system, we know from the third law that S at t equals 0 is 0. Let's assume we don't have some weird ground state degeneracy thing, which is kind of unusual. We can then perform a series of experiments, right, where at many temperatures, we can measure CV at each temperature. How do we do that? Well, we take some little piece of stuff and we tack a thermometer onto it of some kind, and we dump in a known amount of energy, and we look at the temperature rise. You can just do this experimentally. I can tell you, Professor Morshon, for example, has a setup in her lab for doing exactly this on many materials. So you can go and do these measurements, and what you find, basically, right, is that because essentially for each one of these little measurements, delta S over delta T is going to be the heat capacity, because these are all at constant volume, right? What you can do, that's true, right? So what you can do is you can basically say that the entropy at any given temperature minus the entropy at t equals 0, which is probably 0 unless we have some weird ground state degeneracy, that's just going to be the integral from 0 to whatever given temperature you care about of the heat capacity. This is my dummy variable of integration, right? So at any given temperature, I can measure the heat capacity. I can take that quantity, divide it by that temperature, and I can do this measurement a zillion times and add all those up. And that will tell me my change in entropy if I do that over a broad temperature range, right? If in case you're curious, section 4.6 in Rife actually does an example related to this. But so this is how you actually experimentally can determine the entropy for a system. So the entropy may be this thing that it's useful to think about in the abstract, and we have this great statistical mechanics definition for it, but it is possible to actually experimentally determine it in the same way that it's possible to experimentally determine the internal energy of a system by knowing conservation of energy and doing a bunch of careful measurements. All right, hang on one second here. Okay, there's a couple of more things I want to talk about before we start doing general variable manipulations related to this issue about what the natural variables for things are. Okay, so I should tell you, remember I told you I considered the ideal gas law to be an equation of state. Callan is one of these people who actually is pretty uptight about definitions. And his definition of equation of state is something we want to talk about for a second here. He says it relates intensive parameters. And so that would be, examples of that, of course, would be the temperature, the pressure, the chemical potential, in terms of extensive parameters. Now, by that definition, the ideal gas law doesn't fit, right? But what would fit would be if we were able to write down something like the temperature is a function of energy, volume, and particle number, right? So remember, if we can start with the entropy of E, V, and N, right? Take a derivative, and we can say that 1 over T is partial S, partial E at constant V and N. So actually doing this, if I had an actual expression here and I actually did this procedure and inverted this and found T, that would give me what Callan calls an equation of state, right? Now remember, anytime you take a derivative, you're throwing away information, right? If I have a function and I take its derivative, I'm throwing away any knowledge of, say, a constant offset to that function. Just from the derivative, I can't reconstruct the original function. So equations of state do not contain complete thermodynamic information about a system, right? This, the original formulation of S, or I could flip it around and have it be E as a function of S, V, and N. I can invert that function. That actually contains all the information about the system. Anything you'd want to know, it's in there. But this equation of state, we've thrown some information away because we've basically taken a derivative. Let me go on and do a little bit of an example about doing these kinds of variable manipulations, and we'll talk about specific heats again in a second here. All right. So let's talk about the energy. We've already used this once, right? Of an ideal gas. I gave you the spoiler about what the actual final form of the energy is. We're not actually going to derive it completely from first principles yet. We will eventually get there. But here's the question, which one of you asked, right? I asserted that the energy of an ideal gas was independent of the volume. So does E as a function of, say, temperature, volume, and particle number, and again, this is a little weird, we've somehow changed variables, does E depend on the volume at all? And the answer ends up being no, and we're now going to prove that. All right. I told you before it's not the case, and in fact I gave you an expression, and I said for a monatomic ideal gas, it's 3/2 N K Boltzmann T, monatomic, right? I told you that, and we're not going to derive that yet, but the point is we can actually prove, knowing what we know now, knowing the ideal gas law, that the energy has to be volume independent. So let me do an example, and we'll see how we do that. So if I imagine that I'm able to write energy in terms of these variables, you see a lot of thermo involves variable changes. If I could write the energy this way, right, then I can always talk about small changes in the energy. Let's ignore particle number for a second here. Let's work with a fixed number of particles, fixed N, right? We're just going to leave that alone. And I'm going to say any change in energy then has to be from two possible sources. I can have a change of the energy with respect to temperature, a constant volume, and a change in temperature. Or I can have a change of the energy with respect to the volume at constant temperature, change in volume. And I'm telling you what we're going to do is we're going to find this, and we're actually going to find that it has to be zero, based on simply math and the ideal gas law, right? So what we also know that if we think about S of T, V, and N, right? And again, I've done some variable change. You can imagine I find the temperature as a function of the energy. I can invert that, find the energy as a function of the temperature, plug it into my S as a function of E, V, and N, and I can write S as I can just do the variable change and write S as a function of T, V, and N, right? So if I could do that, then I can basically say that ds would be partial S, partial T at constant V dt plus partial S, partial V at constant T dV, right? These are the two ways I can change the entropy. If entropy, I'm fixing N. If all I can vary are temperature and volume, then I can have how the entropy depends with temperature and how the entropy depends with volume. So all I'm doing is basically a tiny bit of calculus here so far, right? Now, from the first law, we know that basically T ds minus P dV equals dE, right? Which means I can manipulate this a little bit, and I can just say that ds equals 1 over T dE plus P over T dV, right? Just double checking that I've got my signs correct here. Okay, and if I use the ideal gas law, I can write this as 1 over T dE plus N K Boltzmann over V dV, right? This is, so I'm using the ideal gas. Okay. All right. So I have that this is ds. I have an expression for dE, and I'm going to plug that expression for dE in here. If I do that, I now can say that ds is 1 over t partial E partial t at constant v dt, okay? Plus a bunch of other stuff, right? We plug in, and it's going to have in it 1 over t partial E partial v with respect to t plus n K Boltzmann over v, and all of this times dv, okay? All right, so that means that this bit, which we already knew before, this is partial s partial t at constant v, and this whole thing here has to be partial s partial v at constant t, right? Now, we're going to use the fact that that mixed partial derivatives should be equal for nice functions, okay? So this is a nice function. I told you entropy was a nice function, which means basically a second derivative of s with respect to t with respect to v has to be the same as the second derivative with respect to v with respect to t, right? Equality of mixed partial derivatives, as long as there's no branch cuts or weird non-analytic stuff going on with the function s as a function of these two variables, this has to be true, okay? Which means I should be able to take the derivative of this thing with respect to the volume, and I should be able to take the derivative of this thing with respect to the temperature and set them equal to each other. And they really have to be mathematically equal, right? So what does that end up looking like? Well, if I go and I do this, I can take this first bit here. That's going to give me this bit here is going to end up giving me partial with respect to v, partial s, partial t at constant v, is going to give me 1 over t, second derivative of e, and then we're going to have partial t, partial v, right? So that's all good. So that's this bit. And now I'm going to take this thing, and I'm going to take its temperature derivative, right? And that's going to give me two terms. First, it's going to give me, so partial s, partial v with respect to t, and I'm going to take a derivative with respect to temperature of that thing. If I take a temperature derivative of this bit, what am I going to get? I'm going to have two terms. I'm going to have minus 1 over t squared, partial E, partial V, constant t. This does not depend on temperature, so it's going to go away. And then I'm going to have plus 1 over t, second derivative of E with respect to t and v, right? So that is the same as that. And this part, for the partial derivatives to be equal, has to go to 0. And I didn't specify the temperature. So the only way this can go to 0 is if the dependence of the energy on the volume at constant temperature is 0, right? So mixed partial derivatives implies that the energy has no volume dependence at fixed temperature for the ideal gas. That's pretty cool, okay? And it shows the power of just some basic underlying assumptions about mathematics, and we've actually learned something really physical here, right? If we have the ideal gas law, that was a key thing. We had to substitute in the ideal gas law. We find that the energy of the ideal gas is independent of the volume if you fix the temperature. All right, so I'm going to stop there. Next time, and boy, I hope I'm back in time to do this on Thursday the 14th. Otherwise, I'll be doing another one of these video lectures. Next time, we're going to talk about the specific heat difference, right? So really, what is Cp minus Cv? We're going to figure that out. We're going to talk a little bit about adiabatic processes. And what I mean by that is we're actually going to see, remember I asserted things like PV to the gamma was a constant. We're going to show that. We're going to show that that's true. Okay. And we're going to talk about actually general approaches to thermodynamic variables. So we're going to learn about basically lots of derivatives, but we're also going to learn about thermodynamic potentials. So we're really going to actually see these other things besides, in some sense we had E of S, V, and N. That's just the inverted version of S of E, V, and N, right? This has everything we care about in it. We're going to actually learn about the other ones. We're going to learn about the Helmholtz free energy, which depends on T, V, and N. We're going to learn about the enthalpy, which depends on S, P, and N. We're going to learn about the Gibbs free energy that depends on T, P, and N. And we're going to learn when these things are appropriate and how to flip back and forth between them all. So that's what we're going to do next Thursday. Thanks very much for your attention.